Okay, so where we left off in class today was with the equation F equals BIL sine theta. And we were just starting to look at the hand rule for it. And I said I would start the video with giving you the hand rule. So think about having a magnet, two poles of a magnet facing each other in north and a south. Here's my wire running between them. Let's suppose the current is flowing this way. Let's suppose it's electron current. So the rule says, with the appropriate hand, point your fingers in the direction of the magnetic field. Okay, so point your fingers in the direction of the magnetic field and point your thumb in the direction of the current flow. And when you do that, the force will come out of the palm of your hand. So to demonstrate this, fingers in the direction of the magnetic field, thumb in the direction of the current, and the force is going to come out of the palm of your hand, and in this question, come up out of the page. Okay, so if you're writing it down, with the appropriate hand, point your fingers in the direction of the magnetic field, point your thumb in the direction of the current flow, and the force will come out of the palm of your hand. So this one would be out of the page. So let's just do a couple of others. Let's suppose we have our magnets like this. So this is the south, this is the north, and this is my wire. And let's say the current in the wire is doing a dot, and let's say this is conventional. Okay, so that means my right hand, my fingers need to go, this way, north to south. My thumb needs to come out of the page, and so this guy would be experiencing a force going this way. Okay, so another one I could ask you is I could do, okay, let's go back to here. Let's do our poles like this. We'll do our wire back like this again. Let's say it's conventional current again. And let's say that the conventional current is going towards the bottom of the page. And if the force is going into the page, then which pole must be the north pole and which pole must be the south pole? If the force is going into the page, which of these poles would need to be the north and which would be the south? Okay, conventional current, and I just did that because I wanted to use my right hand. My left hand's holding the iPad. So my thumb needs to go down. So it could go down like that, or it could go down like this. But I said in the question the force goes into the page. So it has to go down like this, which means my fingers are running from this side to this side. And they're the direction of the magnetic field, which always runs from north to south. Okay? So hopefully you're getting the handle of this one, and don't worry, we'll practice more when I see you in person. And you practice quite a bit with the hand rule itself, or with the equation itself. Okay, so that was a force acting on a current carrying wire. But what if it was just a charged particle? Instead of a whole bunch of particles in the wire, what if it's just a single charged particle? So the second one, oh, my thing just flipped over for no known reason. So the second one is, the second heading is a force on a charged particle moving in a magnetic field. Force on charged particle moving in a magnetic field. Okay? So, what do you think it depends on? So let's suppose this is my magnetic field doing this. And of course, you all know that x's are going into the page. And here's my little charged particle, and it's moving this way. What do you think the force on a charged particle moving in a magnetic field is going to be dependent on? There are really four things. One should be the strength of the field. And hopefully you could guess that the stronger the field, the bigger the force. A second one should be the speed of the particle. Actually, it's the velocity. And hopefully you could guess, the faster the particle's moving, the bigger the force. Another one should be the size of the particle. And again, by size I mean size of the charge, not how much it weighs, but size of charge of particle. And then the fourth one is the direction it's moving. Okay, so if we go back and think of our Bill equation, F equals BIL sine theta, we know what I is. We learned about it in our preview of electricity. I is equal to Q over delta T. So if we take this and put it in where I is, F then is equal to BQL over delta T. L is just a distance, and delta T, this is like a velocity then, right? A distance over a time. So F then will be equal to BQV sine theta. What are the vectors here? The vectors are B and V. And so the equation becomes, we rearrange it to get the directions correct, becomes QV cross B, which will then, of course, be F is equal to QVB sine theta. So Q is the charge in coulombs on the particle. V is the speed of the particle, or the velocity that the well, I guess we can say speed because we've now gone to magnitude since we have the sine theta there. So speed of the particle measured in meters per second. So Q charge in coulombs, V speed in meters per second. It's a capital C. B is the magnetic field strength, of course, in Teslas. And theta is the angle between the two vectors, the V and the B, right? It's these two guys that are vectors. So angle between velocity and field. Now you might wonder why I said velocity there and speed up here. I simply said speed because we were only doing the magnitude, okay? And then, of course, then the force is the force on the charged particle that's moving in that field as a result of it moving in that field, measured in newtons, or at least it should be. Now, something that we do a lot in physics, in Science 12.2, is I say to you, prove the units. Prove that when you multiply coulombs by meters per second by Teslas, you end up with newtons. So I want you to pause the video for a second, and I want you to try it. Okay, now we haven't done one like this before, so try it and then turn me back on so I can show you how I'd like you to do it. Okay? All right, am I back on? So the equation is F equals QVB sine theta, and we want to prove the units. So we want to prove that newtons are equal to coulomb meters per second over Teslas. So to do this, you need to sub in for things. So keep the newtons the same on one side and sub in for different things and cancel out. So the first thing we're going to sub in for is a Tesla. And in the yesterday's class, we learned that a Tesla is defined from our BIL equation. So B is equal to F over IL, which tells me that a Tesla is equal to a Newton over an amp meter. And so where a Tesla is here, I can now sub in a Newton over an amp meter. And when I do that, the meters will cancel. Now the next one I need to remember, and only sub one thing in at a time, is I need to remember I equals Q over delta T. This tells me that a coulomb is equal to, an amp is equal to a coulomb per second. Or, so if you want it, you could say a coulomb was equal to an amp second. And so now where the coulomb is, you could fill in an amp second over a second times a Newton over an amp. Seconds cancel, amps cancel, a Newton is equal to a Newton. So see how you only do one sub at a time, but you got to prove what your sub